So previously we have seen the demand paging. Demand paging is actually when the pages are needed, then only they are loaded into the main memory, and the function which actually loads into the main memory is known as swapper or pager. Okay, and now we'll be seeing the basic concepts needed for this demand paging. With swap, actually we have two things to understand here, which are very basic. Number one is if the page is already in the main memory. If the page is already available in main memory, then it is known as memory resident. If the page is not available in main memory, then it is not memory resident, right? So if the page is memory resident, then the operation is simple. It is like previously we have seen in chapter number 9, right? In chapter number 9, right? We have already seen the paging. If the page is memory resident, then it is simple and it is like paging function. But if the page is not available, then it is different. So we need some new functionality, memory management unit, new functionality to implement for the demand paging. Okay, so however the page, however the implementation is done using the swapping operation, right? We know that swap in and swap out. I have already told you that swap in and out. Previously we were swapping in and swapping out entire process, right? But now we are only swapping in and swapping out the pages of application. Okay, so a part of application, a routine, some routines of applications, not the entire application. Okay, so if the page is not memory resident, then what we need to do, we need to detect and load the page into memory from the storage, right? From the secondary storage. If the page is not available, then we will locate the secondary storage. A trap is generated to the operating system. Operating system will locate the available page in the secondary storage, and it will return the request for the main memory. Okay, and then main memory will update the page table. So we'll see in next slides without change, but this should be done without changing the program behavior. It means that for some time we will abort, we will pause the execution of program, and then when the page will be loaded into the main memory, then it should restart from there, right? So there should not be any change of the behavior of program. It means it should not restart from very beginning. It should start from only the statement or only the page where we left, right? And without programmer need to change the code, and programmer should also not need to change the code. We know that virtual memory management is actually handled by operating system, so any programmer should not deal with should not have to recode or maybe design the algorithm which should specifically be used for this virtual memory allocation. Okay, so these are two concepts we need to know for now. Now, how does this work? What is the new algorithm we need for MMU? So here is that we add one extra bit, valid and invalid bit, into our page table. Now we know that we are having only one entry frame number, right, corresponding to the page number, right? But now what will happen that we have a valid and invalid bit. Valid bit is when there is a page which is requested and it is available in the main memory, then that bit is valid bit, right? Then that page has a valid bit indicator here. For example, if we have a process, okay, and it might have 1, 2, 3, 4, 5 pages, right? And let's say when it is loaded into the main memory, there are 3 frames which should be loaded into the main memory, while their execution, for the execution. So let's say maybe A, B and C, these are loaded into the main memory. So it means that this valid indicates that this page is available into the main memory. Okay, this page is available into the main memory at some location. Okay, maybe this page is available in some location, right? So these pages are available at some location, but for example, a new page is requested, and when we try to locate that page is invalid. Now what will happen that this page request will be aborted, right? Abort. Okay, it will be aborted for some time, and this will generate a request to the our secondary storage, right? Because everything is available over the secondary storage, and that page which were requested over here will be loaded into the main memory. Okay, and then main memory will update the entry of the page table, because now it's available in the main memory. Right now we know that this new page is also available in the main memory, so this entry in the page table is actually updated. So let's say D, let's say we are dealing with here D, right? And so the D is brought over here, and then the D page will be now. If next time we'll need this D page, then we know that it's a valid page. So this is what the valid and invalid bit, which helps us to locate the pages available in the main memory. Now this operation, and now there are when we abort, right? For example, when we requested the D page and it was not available, then there is a page fault. Okay, then there is a page fault. When page fault occurs, we abort. We perform abort operation, right? Now on the page, and when we abort operation, right? Abort operation, and then we request this page from the secondary storage, right? We request the page from secondary storage. Okay, once the secondary storage found this page, then it is will swap in from secondary storage to the main memory and will update this entry, right? So actually this request is a trap, right, which is generated for the operating system. For operating system, we know that this is the virtual memory is actually dealt by operating system. So the trap is actually generated for the operating system. So during MMU address translation, if a valid or invalid bit in the page table entry is I, then the page fault is generated, right? So page fault is generated, right? Page fault is very important here, and it should one thing more you should note that when a page fault is generated, then actually the process is aborted, right? It is paused actually. It is not completely stopped, right? It will not restart from very beginning. It will restart only from this statement. So we shall preserve the state of the process also. Okay. Now here is the same thing shown here. If we have A, C and F pages loaded into the main memory, and we know that these are the locations, valid locations of the page. But if suppose if we want to access an invalid location, then what will happen? A trap will be generated to the operating system, and operating system will locate a new page, and it will again bring it back into the main memory, and then main memory will update the page table also. Okay, so that next time when we will use this, we can access it like paging only, right? Not page on demand, because it's now available into the main memory. Okay, so steps in handling the page fault. There is, if there is a reference to the page, first reference to the page will trap generate a trap to the operating system. We'll see this from this diagram. These are the 6 steps actually. These are the 6 steps of handling with the page fault. So number one is that, for example, this is what we need to load aim. For example, there is some page which is aim, let's say, which has aim data, and we need to load this page into the main memory. Now what will happen, this when this page will be required, it will first see into the page table either it's available or not. Now we have seen that bit I, right? It means that it is not available, it is invalid for this memory. It don't recognize the page. So what will happen, this will ask from the operating system. A trap is generated. The second step is a trap is generated to the operating system. Now operating system will look into the secondary storage, right? Because the operating system is available over the secondary storage. So operating system will see into the secondary storage. When it found the aim page, right? Then it will bring that page into the free frame location. And once it is available in the free frame location, the fifth step is to update the entry into the table and reset the table, right? And then restart the instruction from where we left. Okay. So this is the entire process with 6 steps we have seen previously, right? These are the 6 steps, 1, 2, 3, 4, 5, 6, right? 6 steps, and this is what the graphical representation of the page fault, how the page fault works. So we have also free frames with that, because we know that free frames are allocated for the physical memory. Then there is actually a free frame list in the main memory, right? We know that non-contiguous memory is a memory location over is a memory allocation which can be spread throughout the entire memory, right? So we can write one page on page number 6, one page on page number 80, one page on page number 70, right? So the pages should not be in contiguous manner. That's why we have different page numbers. To manage this, we have a free frame list. Free frame list is you renumber or reorganize the pages in a way that these pages are in a linked list, right? And similar to zeroed linked list, right? It means that 7 would be considered as a 0, and so on. We will be growing the free frame list, right? So this is like a header and the head and the tail, right, of the list. In this portion is actually head of the list, and maybe forward there is a tail of the list. So the starting location is 0 to all, and when we start to refill them, then we start from this zeroth location. And if this is the 0 now, and we have written some page over here, then in next iteration this will be removed from the frame list, and this will be starting, this list will be starting from the 97, and then 97 would be considered as a 0 on the list. Okay. And why these are irregular number? Because 7 is here, then 97, and then 15, then 126, and then again 75, because the pages are actually getting free. When they are getting free, they are actually added into the main memory. Now, for suppose at the beginning 7 and 97 were only 2 pages were available in the memory, so we have created a list of these 2, and then 15 was has become also free. Then we add the 15 to the list. Then 126 was has got free resources, right? We got free resources of 126 location. Then 126 is loaded. So the numbers cannot. It is not necessary that we resort them. These numbers are not sorted. These are added as they are, because if we sort them, then it is again an overhead. So we just add as they are available, as they are getting free from the in the main memory. Okay. So this is the free frame list, which is actually used to allocate the resources in demand paging also. Then we have next thing is copy and write. Now we have, for example, we have a parent, right? Previously we have a parent here, a parent process, and then we want to generate a child process. Then what happened? We use a fork system call. This fork system call, right? This fork system call, but generate a child process which is exactly copy of the parent process, right? So we generate a child process. For example, this is parent process. Maybe this is a library, right? And this is maybe some data. So exactly same data will be copied over here, right? Library and data, right? So for example, this is 2 KB, this is 2 KB, and this is 1 KB. The process is 5 KB, right? And similarly, this will be also 2 KB, this will be also 2 KB, and this will be 1 KB, this will be 5. So because these two are exact copy, right? These two are copy, right? Copied. This is, if this is parent and this is child, then parent is exactly copied from the the child is exactly copied from the parent. So both of the processes are containing exactly same data. Now if we see that these 4 KB's data is actually duplicating in the main memory. So we shall have something to save this space, these 2 extra bits which are actually wasted over here. We have a functionality of copy and write for that in the virtual memory management, right? This is when copy and write allows both parent and child process to initially share the same page in the main memory, right? It means that now what we'll do, we'll not copy the exact, but only we create some reference, right? For example, this is parent process and it has some libraries, and this is the child process. We don't copy, but we leave some references here, right? And these references will locate to the this memory location, right, in the parent process. This is parent and this is child. So we don't bring the entire pages over the we don't copy the entire process here, but only we keep the references to the memory location where these pages are available. Okay, so we don't have the extra burden over the main memory. Okay, if either process modify a shared page, only then the page is copied. Now for example, if this is page A, this is page B, and child process wants to modify the B, then the copy of B will be created here, right? Then a copy of B will be created here, right? Now this page and this B and this B, these two B are different, and parent will still look at this B, but the child has lost this reference, and it is now only looking into the B which is being modified this child. Okay, so COW allows more efficient process creation as only modified pages are copied. In general, free pages are allocated from the pool of zero field on demand page, right? We have seen the list. Pool always have free frames for fast demand execution. Okay, and there's an example shown here. It is very good example that before process 1 modifies this page C. Now for example, we have two processes, process 1 and process 2. Let's say one is parent, one is child. Maybe process 1 is parent and process 2 is child. Now we know that in physical memory they are referencing to the same location. It means that it is not referencing to the different location. If it is referencing to the different locations, then what will happen, that this page is for process 1, this page is for process 1, and this page is for process 1, and this is for process 2, and this B is for process 2, and this C is for process 2, right? So if in the previous approaches if we use those approaches, then in the references would also generate some new location, also occupy some new location over the physical memory. But now we have an algorithm, we have an approach to actually share these resources, right? So these two processes are actually sharing the same resources, right? Sharing the same resources. Now these can be data structures, these can be libraries or something, some routines, etc. Okay. Now this is actually before the modification. Now first of all, P1 tries to modify something. Maybe it wants to modify page C. Then what will happen? That you can see here clearly that if C is being modified by process 1, then only process 1 is the referencing to this copy of C, right? While process 2 is still accessing this C. This C is still valid for process 2, but it's no more available to process 1. So process 1 can only access this page C, right? So this is what the copy on right. And page replacement, we know that actually we are replacing some page. Now for example, if a page fault has occurred and the memory is not always big enough to accommodate all the pages, all the page faults, right? As we know that we are increasing the degree of multiple processing, and so eventually at some time we will run out of the memory. If we will keep on increasing the processes and we will keep on loading the pages into the main memory, then what will happen that we will at some time we will be in states where we cannot load more needed pages, right? So we have to replace the pages. It means that the pages available in the main memory are again reclaimed, right, for the removal, right, for the removal from the main memory. Okay. So we will again modify the bit from valid to invalid. The same process goes, and we'll replace the pages. Okay. So, for example, need for page replacement. Here's what the motivation for the page replacement. For example, if we have a process 1 and process 2, right? We have two processes and we have two process table. A process table, maybe process 1 is from here to here and process 2 is from here to here. Now for example, if I need B, but that B is invalid into the process 1 table, then what will happen? A trap will be generated, right, to operating system, and then operating system will allocate this to free frame list, right, free frame list, but we don't have any page free up here. So what will happen? That it will be not allocated to any location. To handle this, we have a page replacement. We have several page replacement algorithms, like least recently used, right, and we have also FIFO, where we eliminate the first in page from the memory, and then we can free up some space to allocate this. While this least recently used is more commonly used in page replacement algorithms, and once, for example, let's say the C is not used in recent times, then this will be removed. Now the C which were here will become I, and this B is written over here, right, and this B will become V. Okay, so this is the page replacement. So basic page replacement is that when you try to remove some pages, like here, when you try to remove some pages, that page is actually marked as a victim page, and you change from valid bit to invalid and reset the page table, right? So this is the same process which I have already told you. Okay, and allocation of frames. We have another thing is allocation of frames. Actually, uh, to show you that a process, let me come here. For example, if we keep on adding the pages into the main memory, then at some time we will run out of the main memory. So we have to set some certain limit of the process. The minimum limit, that how many pages should be minimally loaded into the main memory so that the process can execute gracefully, right? So we need some minimum number of the pages and we need some maximum number of the pages. While maximum is of course the total frame of the of any process, right? But the minimum is the number of the pages which are only required for execution, right? For example, this is in the process and it needs only 2 pages for execution, minimum 2 pages for execution. Then this will, and maybe then we maybe allocate a 4 page slot, right? 4 page slot to this process, right? Let's say P1, right? And we have another P2, right? P2, and we have only this process maybe needs 3 pages minimum for execution, and so we allocate this 4 or maybe 5 pages, right? So this is actually frame allocation, that how many frames we allocate to a particular process for execution, right? So this can be fixed or can be also be priority. So as we are dealing here, we are using fixed number of frames for a particular process, but it can be also on priority, okay, priority basis. So if now for example this is allocated for only 3 pages and 2 pages are for execution and 1 page is when it is loaded when it is needed, right? For example, this process has maybe 8 pages, I don't know how many pages I have done. So 2 pages for execution were already loaded, these are already loaded. Now from 8 pages, whenever a page is needed, that is loaded into the main memory, and when another page is needed, then it will replace this page. So it will not go beyond its limit. It will replace this page by the with the new page, and when another new page will be needed, that page will also be replaced with a new page, right? With this page, with the page which is actually existing here. So this is what the frame allocation and frame replacement. Frame allocation is when you set some limit for minimum and maximum, right? We set some limit for minimum and maximum. Minimum is when how many pages, how many instruction a process minimally need for execution, right? And maximum is actually most obviously the total number of frame. A process would always need entire process to be loaded into the main memory. So maximum is total number of frames most of the times, okay? So this is what the page allocation. This is page allocation. No, sorry, frame allocation. Because we are talking about the main memory, so it's frame allocation, and this is the page replacement. Okay, where we shuffle between the pages, where we swap between the pages, swap in and swap out the pages. That's what the page replacement. Because we have a limited slot for every process. Okay. So this swapping can be, this replacement can be global, can be local. Global means that we can even take some pages of another process also, and from this is actually open, while local replacement is when you only replace from the given slot. Now in previous slides I have shown that we were only replacing the we were performing actually local replacement, but this replacement can also be done on global basis, right? It means that for the entire memory, we can also do that replacement. So there are two replacements, the local replacement and the global replacement of the pages. The last thing is thrashing. Now thrashing is very important here because as we know that everything has some certain limits, right? And if we keep on loading the processes, and we know that initially when we load a process, there is always a page fault generated, right? If the page fault are so much frequent and the rate of page fault is high, then uh, we will be running out of the main memories at some instance, right? So what will happen, there is a very famous curve for showing this thrashing, is that uh, for example, we keep on loading the we keep on generating the page fault, right? And we keep on loading, right? Keep on loading, keep on loading. What will happen at some time, this will reach to its maximum, right? This will reach to its maximum level. CPU utilization will reach to a some its certain maximum level. Then what will happen, that a sudden drop will be seen in this behavior, right? Which actually which means that actually some the system will stop, right? Which system will stop or maybe crash, right? So this is actually degree of multiple programming, right? We are keep on loading the new processes, keep on loading, keep on loading, keep on loading, but we have some limit because we cannot deal with many page faults. If there are so many page faults, then CPU will be always busy in dealing with the page faults, right? CPU will be always busy in dealing with the page fault, while it spend less time to do its core job, to do processing. It will be always dealing with the page fault. So, for example, if there are 20 processes loaded into the main memory, then every process is actually generating uh, some page fault, right? At some time, every process is generating some page fault. So CPU will be keep on busy to deal with the page faults, not with the processes. So this is an overhead, and this overhead is known as thrashing. A process is busy swapping pages in and out. That's what the swapping is. And we can limit this by using local or priority page replacement, as we have seen previously. So this is about the chapter 10, and I hope you have understood. I hope you have taken this and up to a required level of understanding, and we'll be discussing the your questions and your concerns in the online session. Thank you.